Welcome to this rigorous scientific lecture on how to use artificial intelligence to learn faster from failures through systematic after-action reviews. Let's start with a fundamental question. Why do humans repeat the same mistakes? We have approximately 86 billion neurons capable of pattern recognition, yet we fail to extract lessons from our errors consistently. Without systematic processing, our brains store failure events in episodic memory without extracting actionable rules. The failure enters, gets processed emotionally, but no structured learning loop is created, leading to repeated mistakes. Research shows that without structured intervention, human error rates plateau. In aviation, before systematic reviews, the accident rate per flight hour remained essentially flat for decades. After-action reviews, or AARs, originated in military contexts and have been scientifically validated to reduce error repetition by up to 70% when properly implemented. The learning rate can be modeled as K times structured reviews divided by total failures, where K is a constant representing review quality. Traditional AARs depend on fallible human memory or time-intensive and suffer from cognitive biases like hindsight bias and confirmation bias. Artificial intelligence, particularly large language models, can process failure data at scale, identify patterns humans miss, and generate structured insights with minimal bias. Let me introduce a scientifically rigorous template that combines human judgment with AI processing power. This template has 4 critical components. The template flows sequentially. First, we capture complete context. Second, we perform root cause analysis. Third, we generate exactly one actionable rule. Fourth, we track whether this specific mistake pattern recurs. Context capture is the foundation. We need to record what happened, when it happened, who was involved, what the intended outcome was, and what the actual outcome was. You provide the AI with a structured prompt. Here's the exact format. Describe the failure event in detail. Include timestamps, people involved, decisions made, information available at the time, and environmental factors. Let's use a concrete example. On March 15th at 3 p.m., you deployed a code update to production. The deployment caused a database connection pool exhaustion. Service was down for 47 minutes. 12,000 users were affected. This context document contains quantifiable data. Notice we include precise numbers: 47 minutes, 12,000 users, 3 engineers. Quantification is critical for pattern recognition. Let me ask you a question. Why does quantification matter so much in failure analysis? The answer lies in pattern detection algorithms. AI models, particularly embeddings and clustering algorithms, work by converting text into high-dimensional vectors. Similar numerical patterns cluster together, enabling the system to recognize when you're repeating mistakes. Mathematically, similarity is calculated using cosine similarity. This is the dot product of vectors A and B divided by the product of their magnitudes. The more specific your numbers, the more accurate the clustering. Now we move to root cause analysis. This is where AI provides the most value. Traditional root cause analysis uses techniques like the 5 whys or fishbone diagrams. The 5 whys technique iteratively asks why until you reach a root cause. But humans often stop too early or go down incorrect causal chains due to cognitive biases. An AI system can simultaneously evaluate multiple causal hypotheses. It can generate 10 possible root causes, rank them by likelihood based on historical data, and highlight which ones you've encountered before. Here's the prompt structure. Given this failure context, generate 5 potential root causes. For each cause, explain the causal mechanism. Rank them by likelihood based on the evidence. Identify if any causes match previous failures in the database. For our deployment failure, the AI might identify these root causes. First, insufficient load testing of connection pool under production scale. Second, missing monitoring alerts for connection pool exhaustion. Third, no rollback plan in deployment checklist. Notice the AI provides confidence levels and identifies a pattern match with the previous incident. This is powerful. It's telling you that you've made essentially the same mistake before, just in a different context. Let's do a quick calculation. How accurate is AI root cause analysis compared to human analysis? Let's model this. The probability of identifying the correct root cause is the probability a human identifies it times the probability the AI confirms it given the human identified it. Studies show humans correctly identify root causes about 60% of the time when working alone, affected by hindsight bias and availability heuristic. When an AI validates a human's hypothesis using pattern matching across large datasets, the conditional probability increases to about 90%. Multiplying these gives 54%. But wait, the AI also generates independent hypotheses. If we add the AI's novel suggestions with probability 0.3 of being correct, we get 0.54 plus 0.3 times 0.4, approximately 66% total accuracy. A 10% improvement in identifying correct root causes translates to significantly faster learning curves and fewer repeated mistakes over time. Now we reach the most critical component, rule generation. This is where we convert root cause understanding into actionable behavior change. This might seem arbitrary, but it's based on cognitive science. Human working memory can reliably hold and implement about one new procedural rule at a time. Multiple rules lead to cognitive overload and implementation failure. A good rule must be specific, measurable, actionable, tied to the root cause, and verifiable. Let's examine each criterion. Compare a bad rule like, be more careful next time, which is vague and unmeasurable, to a good rule like, run load tests with 2 times expected traffic before any production deployment. The good rule is concrete and verifiable. Here's how you prompt the AI for rule generation. Given the root cause of inadequate load testing, generate exactly one procedural rule that would prevent this failure. The rule must be specific, measurable, and implementable immediately. Format it as a checklist item. For our deployment failure, the AI generates this rule. Before any production deployment, run automated load tests simulating 200% of peak observed traffic for a minimum of 30 minutes. Deployment is blocked if connection pool utilization exceeds 70% during testing. We can quantify rule quality using a specificity score. Count concrete parameters like numbers, times, thresholds, divided by total words. Higher scores indicate more actionable rules. Our rule contains these concrete parameters: 200% peak observed traffic, 30 minutes, 70% threshold. That's 4 concrete parameters in a 29-word rule, giving a specificity score of 0.14, which is excellent for procedural rules. The final component closes the learning loop. We must track whether the same mistake pattern recurs after implementing the rule. This is where AI provides continuous monitoring. Every failure event gets converted to a vector embedding. New failures are compared against the historical database. If cosine similarity exceeds 0.8 with a previous failure, the system flags a recurrence. The new failure passes through an embedding model, gets converted to a vector, and is compared against all historical failures. When similarity exceeds threshold, the system alerts you that you're repeating a mistake. This creates accountability. If the same pattern recurs, it means either the rule was not followed, the rule was insufficient, or the root cause analysis was incorrect. Each of these tells you something important. Let's quantify how effective this system is. We can model learning as a decay in error repetition rate over time. The repetition rate R at time t equals the initial rate R0 times e to the negative lambda t, where lambda is the learning rate constant. Lambda equals rules implemented divided by mean time between implementations. More rules implemented faster increases the learning rate. Organizations implementing this system report error repetition rates declining with a half-life of approximately 3 months. Traditional AARs show half-lives of 12 to 18 months. The half-life formula is natural log of 2 divided by lambda, approximately 3 months with AI assistance versus 12 months without. That's a 4 times acceleration in learning. Let me give you an analogy from aviation. Flight simulators allow pilots to experience failures in a safe environment. The AI AAR system is like a simulator for your decision-making process. Flight simulators let pilots practice emergency procedures without risk. The AI AAR system lets you extract maximum learning from real failures without repeating them. Both compress decades of experience into months. Commercial pilots spend over 100 hours in simulators, experiencing every possible failure mode. This compressed experience is why aviation has such low accident rates, 1 fatal accident per 7 million flights. By systematically processing every failure through this AI-AAR template, you compress learning that would normally take years of repeated mistakes into months of deliberate practice. Let me walk through a complete real-world example with a software engineering team that implemented this system for 6 months. In the 6 months before implementing the AI-AAR system, this team experienced 23 production incidents. Of these, 8 were repeats of previous failure patterns, a repetition rate of 35%. They implemented the 4-component template. Every incident got full context capture, AI root cause analysis, 1 rule generation, and embedding-based tracking. After 6 months, total incidents dropped 17% to 19. More impressively, repeat incidents dropped 75% from 8 to just 2. Mean time to resolution cut in half. The team generated 19 high-quality rules with 89% compliance. Let's calculate the economic impact. Each incident costs approximately 5 engineer hours plus revenue impact. With 6 fewer repeat incidents, that's 30 engineer hours saved, plus the faster resolution time saved an additional 10 hours per incident. Total savings, 30 hours from prevented repeats plus 9.5 hours from faster resolution equals 39.5 engineering hours over 6 months. At $100 per hour, that's $3,950 in direct cost savings. The real value isn't the immediate savings. It's the compound learning effect. Each rule implemented makes future failures less likely. Each pattern recognized speeds up future debugging. This compounds exponentially. Now let's discuss how to implement this system in your organization. You need 4 components: an AI interface, a structured database, an embedding model, and a discipline protocol. You can use any large language model. GPT-4, Claude, or open-source alternatives like Llama all work. The key is consistent prompt engineering and structured output formatting. Use a simple spreadsheet or database. Columns: date, context description, root causes, generated rule, embedding vector, recurrence flag. Each failure gets 1 row. Here's a simple example. Each row captures 1 failure. Notice row 3 shows a recurrence match with incident number 1 flagging that we're repeating a pattern. Most AI APIs provide embedding endpoints. Send your context description, receive a 1536-dimensional vector. Store it. For new failures, compute cosine similarity against all stored vectors. This is the hardest part. You must commit to processing every failure through the template within 24 hours, no exceptions. Discipline beats intelligence in learning systems. Let's examine the neuroscience underlying this approach. Why does structured review enhance learning compared to informal reflection? Memory formation involves encoding, consolidation, and retrieval. Structured review enhances each stage through deliberate attention, emotional tagging, and retrieval practice. The AAR template forces deliberate encoding by requiring detailed context capture. It enhances consolidation by extracting causal patterns. It creates retrieval practice through recurrence tracking. Cognitive science research demonstrates that spaced retrieval practice increases long-term retention by approximately 300% compared to passive review. The recurrence tracking component implements spaced retrieval. Memory retention probability decays exponentially with time constant S. Each retrieval event resets the timer and increases S, making the memory more durable. The hippocampus in your brain consolidates memories and detects patterns. The AI-AAR system acts as an external hippocampus with perfect recall and unlimited pattern matching capacity. Let's discuss the most common mistakes people make when implementing this system and how to avoid them. People want to extract maximum learning and generate 5 or 10 rules per failure. This guarantees implementation failure due to cognitive overload. Stick to exactly 1 rule. Be disciplined. Rules like be more careful or pay closer attention are useless. They can't be verified, can't be tracked, and don't change behavior. Every rule must have concrete numbers and verifiable outcomes. Some teams do great root cause analysis and rule generation, but never check if mistakes repeat. This breaks the learning loop. You must close the loop by tracking recurrence. When failures occur, there's often pressure to blame individuals. The AAR process must be blameless and focus on systemic improvements. Psychological safety is prerequisite for honest reporting. Once you've accumulated 50 or more AARs, you can perform meta-analysis to discover higher-order patterns. What types of failures occur most frequently? What rules have highest compliance? What root causes cluster together? After analyzing 100 AARs, you might discover that 32% of failures involve integration issues, 41% trace to insufficient testing, and automated checks have 94% compliance versus 67% for manual reviews. These patterns reveal systemic weaknesses in your processes. If insufficient testing causes 41% of failures, you need to invest in better testing infrastructure, not just add testing rules. You can calculate return on investment for prevention measures. Failures prevented times cost per failure divided by investment in prevention tools or processes. This AI-AAR approach connects to several important concepts in learning theory. Let's explore these connections briefly. Anders Ericsson's research on expert performance shows that deliberate practice, not just experience, drives skill development. The AAR template creates deliberate practice by forcing focused attention on specific failure modes. Chris Argyris distinguished single-loop learning, which corrects errors, from double-loop learning, which questions underlying assumptions. AI-assisted root cause analysis facilitates double-loop learning by suggesting non-obvious causal chains. Nassim Taleb argues that some systems gain from disorder and stress. The AAR system makes your processes antifragile. Each failure makes you stronger by adding a new rule to your playbook. Fragile systems break under stress. Antifragile systems grow stronger. The AAR process converts your organization from fragile to antifragile by building immunity to previously encountered failure modes. Let's do one final back-of-the-envelope calculation. What's the total impact of implementing the system for 1 year in a 20-person engineering team? Assume a baseline of 50 incidents per year, industry average for teams of this size. With 35% repeat rate, that's 15 repeat incidents annually. Each repeat costs approximately 8 engineer hours to debug and fix. The AI-AAR system reduces repeat rate to 5% based on empirical data, so only 2.5 repeat incidents per year. That prevents 12.5 repeats. Time savings: 12.5 prevented repeats times 8 hours each equals 100 engineer hours saved annually. Plus, faster resolution from better debugging patterns saves approximately 30 minutes per incident. That's 25 additional hours saved. Total savings: 125 engineer hours at $120 per hour, fully loaded cost, equals $15,000 per year in direct savings. The indirect benefits are much larger: reduced customer frustration, faster feature velocity, improved team morale, and accumulated knowledge capital. These easily multiply the direct savings by 3 to 5 times. Conservatively estimating, total value ranges from $45,000 to $75,000 annually for a 20-person team. The cost to implement is maybe 20 hours of initial setup plus 30 minutes per incident. Return on investment: $60,000 value divided by 45 hours of effort times $120 per hour equals approximately 11 times return. That's an exceptional ROI for a learning intervention. Let me summarize the key scientific principles and practical takeaways from this lecture. Cognitive science shows that structured review protocols extract significantly more learning from experience than informal reflection. The 4-component template provides this structure. Human memory is fallible and biased. AI provides perfect recall and unbiased pattern matching across large datasets. This makes recurrence detection possible. Cognitive load theory tells us that working memory limitations constrain behavior change. One high-quality rule per failure ensures implementation. Specific numbers and context descriptions enable embedding-based similarity matching. Vague descriptions prevent the AI from detecting repeated patterns. Recurrence tracking closes the learning loop and creates accountability. Without tracking, you can't verify whether your rules actually prevent repeats. Here's your implementation checklist. Start with these 5 steps. Choose an AI platform, create standardized prompts for each component, and test them on past failures. Build a simple spreadsheet or database with required columns. Include embedding storage. Make a team commitment that every failure gets processed through the template within 24 hours. This discipline is essential. Begin measuring repeat rate, time to resolution, and rule compliance. These metrics prove the system's value. Every quarter, analyze accumulated AARs to identify systemic patterns and high-level improvement opportunities. Looking forward, this approach will become more sophisticated. Future systems will automatically detect failures, generate draft AARs, and proactively warn when you're about to repeat a mistake in real time. Imagine wearing a system that monitors your decisions in real time, compares them to your failure database, and alerts you when you're about to make a mistake you've made before. That technology is 2 to 3 years away. Over decades, individuals and organizations using these systems will accumulate knowledge capital that compounds exponentially. The learning gap between those who use structured AI, AARs, and those who don't will become enormous. Learning faster from failures is perhaps the ultimate competitive advantage in complex domains. The teams and individuals who master this skill will outpace their peers by orders of magnitude. You don't need perfect tools or perfect processes to start. Take your next failure, run it through this 4-component template, and generate one rule. That's all you need to begin. Thank you for your attention in this lecture. Remember, failures are not obstacles but opportunities for accelerated learning when processed systematically with AI assistance.